Hello again, everybody. This is Noah with lecture about light quantum theory. Light and quantum theory. That's a comma. Light and quantum theory, 3.1 and 3.3. Okay, so first thing I want to say is this. She went by this really fast, but it's okay. Don't panic. It's not actually so bad. The point of this lecture was really just getting a summary of if light is in waves or if light is in particles. The answer really is both, but it's understanding which to use where. Okay, so that's all this lecture was telling us, where we want to think of light as waves and where we want to think of light as particles. Okay, so that's the main point, in my opinion. Okay, so in this lecture, we had tons of equations given to us and big numbers and graphs of light and things, and it was all really fast. But don't panic. All the equations in this lecture are on the equation sheet that she gives us for tests. All can be found on the test. And so I'm going to kind of break down each of these, except the speed of light. I'm not going to break down the speed of light. That one's obvious. It's in meters per second. That's easy. Okay, I'm going to talk about Planck's constant and E equals h times frequency together. Okay, and okay, we'll go from there. Okay, so first Planck's constant. Okay, so Planck's constant is this big number, but emphasis on constant, meaning this won't change. And all this is saying is that Planck was trying to emit, see how much energy he can get light to emit. But to do that, he realized that current science at the time was false. They said, they came, and this relates to the black body radiation principle, I guess. People thought that if you heated up a pole, it would keep getting brighter and brighter and brighter and brighter. But we kind of know that's not true. If you heat up a pole, even with as much heat as you possibly can, it reaches a max. There's a point where it reaches its max of light that you heat up. So from this, it peaks, but so because it peaks, Planck found out that light goes in packages of energy, and things emit energy in packages rather than in a constant. So more like steps than in a constant. So how big are those packages? That's where his constant comes in. That's why that's a thing. He's saying that his constant times the frequency is how much energy is being emitted. So if you think about his constant as just 1/2, this is just easier. You can say half the frequency is how much energy is in one of those packages that are being sent out by the sun or a fire or a light, things like that. So Planck's constant, not so bad. Black body radiation is just that things heat up and they reach a peak, and at the peak depends on what color they are. There's more about that I don't quite understand about temperature, but I think that's okay for now. Okay, so those chunks that Planck was talking about are called quanta, hence quantum theory. And so quantum theory, when you hear quantum theory, just think, energy is being absorbed or sent out in packages. How big are the packages? It depends on the frequency. Okay, so frequency is very often related to energy. In fact, we need that. That's essential for telling how reality works. Okay. So, emphasis though, energy is in joules. Okay, a joule, if you've taken physics before, it's just a Newton multiplied by a meter, and that's just work. And then work over time is a watt. If you think about it, WT, and you say it out loud, it's a watt. And a watt is the things you read on light bulbs. like the instructions of the light bulb, it'll say it'll be a 60-watt light bulb, and that just means that that's how much energy over time it's emitting. So don't get confused by units on these. Okay. Okay, the next equation was the speed of light equals lambda, or wavelength, times frequency. Okay, so hey, emphasis, speed of light has to do with frequency, remember that. Lambda times frequency equals the speed of light. Okay, so speed of light, that is a constant, so that's not going to change. So really the only two variables can be here, so it's easy to try and find these, okay? And of course the classic story, have you ever played with the cord on the vacuum? You know, the faster, if you think about it, it takes more energy to do big waves and faster waves than it does to do small waves or slow wave, or small waves or slowly oscillating it, the frequency. And another thing with meters, light, if you remember, is always meters per second, and so lambda is in meters, and frequency is in hertz, which is just 1/second, and so that comes out to be meters per second when you multiply them together. Okay. Remember that all light waves, I had to put in light there, travel at the speed of light, same speed. Okay, now something that she probably went over really fast. I'm going to try and go over it slowly with everybody. The photoelectric effect, okay? This works in solar panels. This is how solar panels work. So I want you to think of a solar panel. Sunlight hits a solar panel, and an electron goes from the metal in the solar panel, okay? So the metal inside is charged, and it gets excited. And so an electron gets sent off. And the electron goes into a wire and then goes to power your house. Okay, so that's how solar panels work. So that's this principle that we're talking about. So it's when a light is shined on charged metal that an electron will leave. So you kind of imagine the electron getting super, super excited that it just jumps out. It just jumps out and leaves the atom and goes and then travels along conductors. So the question is, how much energy does it take to take an electron off? See, so this is the question with solar panels, because the energy coming from the sun isn't quite 100% going into our house. There's a certain percentage, and it depends on the efficiency of the solar panel, but there's a certain percentage that it takes to get the electron to come off the metal at first. Okay, so, and then I drew this. Just imagine which one do you have more energy in. Well, so let's talk about that first. So I have you on a jet ski. These are big frequent waves, and these are long, slow waves. Which one do I like better? To be honest, I like the more frequent more because it's more fun. This is kind of boring when you're like this. But with this, it's more bouncy, and I get good jumps and whatever and stuff. And this has more energy. So just think, the more frequent waves, the more energy. And so when dealing with like something like a solar panel or trying to get electrons off of charged metal, then you want to think that the more frequent light or the more intense light is going to take off more electrons. Okay, so this comes to our last equation that we're working with over here, called the work function. Okay, so it's got this scary looking sign here that I'm just going to say omega, because I'm not entirely sure what that is equal to Planck's constant there, we know, frequency we know, and then kinetic energy we know, just the 1/2 mv squared. If you don't remember physics, then that's just a typical physics equation. Okay, so we're going to learn how that works. So that says, that this equation says that there is a fixed amount per material. So I think this material, it depends, this number right here depends on the metal you're working with. Okay, so a certain metal you're working with takes this much energy, because we know from this equation above that this is just energy, this much energy, and then minus however fast the electron was going. And that's how much energy it took to get the electron off. So to describe that in a better way, I have this piece of metal here. I have sunlight hitting it, and it's charged. So I have so much sunlight hitting it and that sunlight is quantified by how much energy is in that sunlight. And then I reach this point where the electron leaves. So the electron got so excited that he wants to leave now. So I've drawn this little line kind of separating the two different parts. So here we have this omega. And so in this omega, we have to work to get up to that, and then we break out of that fun barrier where the electron's had so much fun that he wants to leave now. Then at this point, we see the energy by how fast it goes. So it's no longer energy quantified by like the intensity or frequency. It's now how fast it goes. So you see that some energy, this is why solar panels aren't 100% efficient quite yet, because some of the energy is going into just getting the electron off. So the energy coming from the sun, part of it goes into just getting the electron off, and then the electron goes and then into the conductors, into power things. So just remember that equation. Again, all these equations are given on the test sheet. So it's just algebra. So since these are all big numbers, just deal with just the algebra of the variables first, and then plug the numbers in. Okay. This equation, what it does is it allows you to take energy and relate it to how fast the electron goes. That's a velocity, not frequency. So these two are different. So energy, and you can tell how fast an electron will go from that. Okay? All right, hopefully that helped clear this lecture up. Comment if there's any questions. Thanks.